let's get started on that warm-up problem. And I give us a function of x squared minus 4. And I asked us to graph it, to label some points, but specifically to find the slope between 1 comma f of 1 and 3 comma f of 3. So let's get started with a sketch. I know that this is a parabola. I know that the coefficient in front of my x is positive, which means it's one of these concave up parabolas. And that minus 4 means that my entire graph has been shifted down 4 along the y-axis. So I'm going to sketch this. And it's not going to be perfect, but, oh wait, we're shifted down on the y-axis. Let me move that. Whatever. It'll be fine. We'll just make it taller. So this whole thing is shifted down 4. So a couple of things to note. This also, I know that I can find the x-intercepts by setting that whole thing equal to 0, meaning that x equals plus or minus 2 are going to be those intercepts. So I know that's an x equals 2 and x equals negative 2, and that is down here at negative 4. I didn't actually ask you to label any of those things, but just for reference, they're going to help us kind of anchor the points that I did ask about. Well, in terms of 1 and f of 1, this notation f of 1 says plug in the 1 where we have an x. So 1 squared is going to be 1 minus 4 is going to give me negative 3. So 1 comma negative 3 is that first point that I want to label. So here's 1, we'll call that down here, 1 comma negative 3. That second point that I asked us to label, 3 comma f of 3. So if I plug in 3 here, 3 squared is 9. 9 minus 4, I get a 5. So 3 is somewhere over here, and I could label that 3 comma 5. And the line that we're talking about then is going between those 2 points. We'll see how good I do. Okay, something like that. And really, this is just my excuse to practice finding slope of the line. Fast forwarding back to finding our slope. So when we're finding the slope of a line, sometimes the phrase people say is rise over run. It's probably better for us to think about this as a change in y value divided by a change in x value. So if I come in here to find that change in y value divided by a change in x value, you can also think about that as like a y2 minus a y1 over x2 minus x1, just giving some different notations. Or when we talk about change in y over change in x, this little triangle is our mathematical notation to mean a change in. Given the points we have, it doesn't actually matter which one of those we sort of call point 1 and point 2. By convention, the point on the leftmost end we label as point 1. And on the right-hand side, by convention, we label that as 0.2. But it won't actually matter as long as we keep them in the same order. So when I find that slope, my y2 minus y1 is going to look like 5 minus negative 3. And then my x2 minus x1, I'm looking at 3 minus 1. So in the numerator, 5 minus a minus is going to make that plus. And 5 plus 3, I get 8. And in my denominator, 3 minus 1, I get 2. So that slope was, in fact, 4. So really quickly, on your paper, if I were to draw the secant line between those 2 points, meaning a straight line connecting those 2 points, what would you get for a slope? Hold on to it. Don't type it in the chat just yet. our change in y over change in x. So that could be 2 minus 1 over 4 minus 1. There's that 1/3 that folks put in the chat. Looks like that is our correct slope. So finding the slope between 2 points on a curve is called the secant line. But the truth is, most of the time in calculus, this was our old school way of finding slope. We needed 2 points. Our goal in calculus is going to be to find the slope using just 1 point on the graph. So I'm going to get rid of the 4 here. That is not the point that I want to find the slope at. In fact, I really just want to find the slope of this curve when x equals 1 in particular. Now, we first have to decide what that means for the graph, the slope at a single point. So if we imagine that we zoomed way in on this graph, like if you were using a graphing calculator, eventually if you zoom in far enough, it's really just going to look straight. And that idea of if we zoom in far enough, just right around that point, it's going to look straight. We call this the tangent line. And that tangent line, depending on where we are in the graph, right? If I imagine if I was at this point, the tangent line would be different because it's the line where we're sort of just touching the graph at that single point, and it approximates the line just right around that point. So if I picked a point over here, my tangent line might look like that. If I picked a point up here, my tangent line is looking pretty flat. So that idea of a tangent line is that it's going to kind of match up with our curve, but just at a single point. Here's how we're going to figure out the slope of that tangent line we were looking for. So we know that we can find the slope by looking at a change in y over a change in x. And if we're trying to find the slope at one particular point, we're going to start with that idea of finding the slope between 2 points. And the way I'm going to do that is I'm just going to fake a new point on here. So that was an x value of 1, but I'm just going to move over a little bit. And how far I'm going to move over, I'm going to move over a hair. I don't really know what h stands for, but we're going to move over just a little bit. So if this was an x value of 1, then when I move over just a little bit, I'm at a value of 1 plus h, as we moved over that distance. So thinking about labeling this as a point or coming up with that y value so we can find the slope, if I were to label this on the y-axis, the x that I'm plugging in is 1 plus h. So this would become the square root of 1 plus h. Now, if I'm finding my slope as a change in y over a change in x, my two y values that we're working with here are the square root of 1 plus h minus 1. My denominator, I'm going to have my x2, 1 plus h, minus my x1, which was 1. Well, in my denominator, this 1 and that negative 1, they're going to cancel out. And I am left with the square root of 1 plus h minus 1 all over h. This is sort of generically my slope of the tangent line, but that doesn't really help us. We're looking for a specific number. So the calculus idea that we're using is this idea of a limit. Right now, if I draw the, let me put the tangent line slope that we're looking for right? My tangent line looks like this. Well, if I think about the slope between these 2 points right here, my secant line slope is not exactly the tangent line slope I was looking for. It's kind of close, but it's not quite the same. So the calculus idea that we're going to use is I'm going to take this point and scoot it a little bit closer to the point where we care about the tangent line slope. Now, if I take the slope between those two new points, it's a little bit closer to the tangent line slope we're looking for. It's not quite right, but it's closer. But if I move my point even closer to the place where I care about the tangent line, now if I draw the secant line slope between those 2 points, you can see that as I move along, those slopes are getting closer and closer to the slope of the tangent line we want. And our math tool for sliding this along and getting closer and closer is a limit. And in particular, what we're doing is taking that distance h between these two and squeezing it closer and closer and closer together, meaning we're looking for that limit as h approaches 0. So if I want to find the slope of this line, the slope of that tangent line is going to come from looking at the limit as h approaches 0 of 1 plus h minus 1 all over h. Let's actually evaluate that limit. I'm looking for a limit as h approaches 0, the square root of 1 plus h minus 1 all over h. First thing we try with any limit problem is to plug the number in. But if I plug in 0 for h, then on the numerator I have 0, and in the denominator I also have 0. So 0 over 0 is telling me to go do some algebra. What kind of algebra? I've got square roots, so I'm going to want to multiply by the conjugate. So if I come in here and I multiply by the conjugate, meaning the square root of 1 plus h plus 1 over the square root of 1 plus h plus 1 again. The whole reason we're multiplying by the conjugate is to hope that that h in the denominator goes away. So I'm not going to multiply the denominator out. I'm going to leave that h alone. I am running into myself over here. I'm going to leave that h alone, get myself some parentheses. Got 1 plus h plus 1. And in the numerator, the reason we multiplied by the conjugate is so that those middle terms would cancel. So I'm going to end up with 1 plus h, middle terms cancel, and then negative 1 times 1 would be minus a 1. The 1 and the negative 1 cancel out. H over h turns into a big giant 1 for me. And now I'm just looking at the limit as h approaches 0 of 1 over the square root of 1 plus h plus 1. Or if I plug in 0 for h, I've got 1 over the square root of 1 plus 1, or 1 over 2. Which means, back to this, the slope of this tangent line, when x equals 1, the slope of that tangent line is 1/2. So before, when we did this problem, we were finding the slope of a secant line between x equals 1 and x equals 3. But now I just want to know the slope of the tangent line at x equals 3. I'm not going to do as great a job with my picture. I'm not going to worry about making it perfectly to scale. A fake picture is going to do me just fine. So here is our point 3, 5. And I am trying to find the actual slope of the actual tangent line right at that point. But our mathematical tool that we're going to use to do that is to scoot away from 3 just a little bit. How much? A hair. I'm going to move over by h to be at the point 3, to be at the x value of 3 plus h. Which means if I were to label the y value here, my y value at 3 plus h is take that 3 plus h and plug it in for x. Plug it in for x. So I would have f of 3 plus h is going to look like 3 plus h squared minus 4. That's my y value at this point. So if I'm going to find the slope of that tangent line, that slope is going to come from the change in y over the change in x. So my y values go from 3 plus h squared minus 4 minus my other y value here of 5. And my x values are going from 3 plus h minus the x value of 3. If we clean this up, I'd have 3 plus h squared minus 9. And in the denominator, the 3h minus 3 is going to leave us with just an h on the bottom. Now, here's the tricky part, which gets back to the question in there. If I want to find the slope exactly at 3, I have to move this point all the way over here to 3, which is the same thing on the x-axis as thinking about squeezing this h down to 0. And the way we write that mathematically is to take the limit as h approaches 0. So our slope here is going to come from taking this limit. So h is going to 0. We're going to be squeezing in on this point 3, 5, but our slope is coming from evaluating this limit. Let's push through this limit problem together. First thing we try with a limit problem is to plug in the value. And if I plug in 0, 3 plus 0 is 3. I'll square that and get 9. 9 minus 9 is 0. We've got 0 on the bottom. So that's going to 0 over 0, which says we better do some algebra. Here, there isn't really anything to factor. We don't have fractions on top that need a common denominator, and we don't have square roots that would need a conjugate. So really our best bet is to multiply this out. So instead of factoring, we're going to distribute it out. So I'm looking at the limit as h approaches 0. So if I FOIL this out, that's the same as doing 3 plus h times 3 plus h. So 3 times 3 will give me 9. 3 times h, I've got a 3h. The other 3 times the other h gives me another 3h, and h times h is going to give me h squared. So when I multiply out that top, I'm going to have 9 plus 6h plus h squared minus 9, and that whole thing is over h. I'm going to clean this up as much as I can, meaning that 9 and that 9 are going to cancel out. And then really in terms of the 0 over 0 with the limit, it's the 0 in the denominator that's the problem. So I'm hoping that it's going to cancel out to give me that 1 again, that I'm going to find something on the top that's going to help me cancel out that h in the denominator. And it looks like I've got it because in the numerator, I can factor an h out. And if I pull an h out, I'll have 6 plus h. In my denominator, I have h. And this is going back to that same idea that h over h is equal to 1 everywhere except exactly at 0. And this limit doesn't mean that we're exactly at 0. It means we're creeping up on 0. I know that that's weird, but algebraically, that's how this is working out. Now I can plug the 0 in for h because we don't have 0 over 0 in the limit anymore. And 6 plus 0, I get 6. So whatever else is going on with the equation of that tangent line, I know this tangent line that touches the graph exactly at that point has a slope of 6. Moved over here, again, that's a distance of h, but I could call this x value 3 minus h because we moved to the left. So if I did 3 minus h, then the y value on this graph would come from plugging in 3 minus h to the function. So now my y value would look like 3 minus h squared minus 4. And if I set the slope up this way, I would still be taking the limit as h approaches 0 because h is the distance between those 2 points. So I'm still letting that part go to 0. So I'm taking the limit as h approaches 0. And my two y values here, convention would have us do that y2 minus y1, moving from left to right, meaning this would be my x1, x2, and sorry, my x1, y1, and this would be my x2, y2. So convention would then have us write this as 5 minus 3 minus h squared minus 4 all over 3 minus 3 minus h. Now if we go to take this limit, I'm going to clean up the algebra as much as I can. So in the denominator, when I distribute that minus sign through, the 3's will cancel and my h will become positive. In the numerator, I'm going to have 5 minus, and I'm going to go ahead and do the part in parentheses here first. So if I FOIL this out, I would have 9 minus 6h plus h squared, and then we've got minus 4. Now I can distribute this minus sign through. Oh, I might as well clean this up first. I've got 9 minus 4, so that's going to be 5. And then I'll distribute the minus sign through. So I'll have 5 minus 5 plus 6h minus h squared all over h. I can cancel out those 5's. And once again, even though I have 0 over 0 for that limit, it's not going to be a problem because we can factor an h out of the numerator. When I pull that h out, I'll be left with 6 minus h, whole thing over h. And once again, that h over h is going to be equal to 1. In the limit as h approaches 0, I now have 6 minus 0 or 6, which matches what we got before. Absolutely, you can go to either side. Mathematical convention and our textbook go with the value plus h or plus delta x. My handwriting's not very neat, so if I do plus delta x, like it gets messy on my paper. That's why I use h instead of delta x. But if you do x minus h, you tend to have to track down a whole lot of minus signs in the problem. And I always figure that that's introducing more possibility for errors. So if I can avoid introducing additional minus signs, I'm going to do that. So without a picture, I know that this slope for our tangent line is going to look like the limit as h approaches 0, right? I don't need the picture to know that I'm going to be plugging in my 2 points, right? So one of those points on the graph is going to be 3f of 3, or 3 comma, when I plug in 3 here, I'll get 1/5. And that other point, I'm going to move over plus h. So my other point is going to look like 3 plus h, comma, f of 3 plus h. And f of 3 plus h says I'm taking 3 plus h and plugging it in for x. So I would have 1 over 3 plus h plus 2. So these are my 2 points that I'm finding the slope between, and then taking that limit, my h got a little crooked, taking that limit as h approaches 0. So I'm going to take that ugly point minus the nice point. And this ugly point, I guess I could clean up because 3 plus 2 is actually 5. So I would have 1 over 5 plus h minus 1 over 5 from here. And then in the denominator, I'd have 3 plus h minus 3. I didn't need that line to be quite so long. So if I plug in a 0 for h right now, in the numerator, I'll end up with 1/5 minus 1/5. Well, that's 0. And the denominator, I've got 3 minus 3, that's 0. And if h goes to 0, that's also a 0. I got 0 over 0. Every time we're doing the slope of a tangent line problem, we should get 0 over 0 for that limit until we do more work. Here's the more work. When I look at that, and with that 3 and the minus 3, I'm going to go ahead and just get rid of those. 0 over 0 is telling us to do some algebra, and because I've got fractions, I know that I need to get a common denominator. So to this 1 over 5 plus h, I'm going to need to multiply that by 5 over 5. And to the 1 over 5, I'm going to multiply by 5 plus h over 5 plus h. So up here on top, I've got 5 over 5 times 5 plus h minus 5 plus h over that same denominator. And that whole entire thing is still over h. Well, the reason to get a common denominator on the top is so that we can combine that into one fraction. So that this looks like 5 minus 5 plus h all over 5 times 5 plus h. Now, I'm running out of board space here, but that whole thing is still divided by h. I'm going to write that whole thing divided by h in a slightly different way, because I can think about that as multiplying by 1 over h. When I distribute that minus sign out, by the magic of my eraser, when I distribute that minus sign out, I'm going to have minus 5 minus h, meaning my 2 5s cancel out, and that negative h over h isn't going to become a positive one, but it is going to become a negative 1. So I'm going to end up with negative 1 on top, and in the bottom, when I plug in 0, I'll have 5 times 5, or 25. So my slope is negative 1 over 25. I've got a slope and I've got a point. So if I need to find the equation of that tangent line, usually most students, their favorite version for the equation of the line is y equals mx plus b. My calculus favorite version is our point slope form that looks like y minus y1 is equal to m times x minus x1. And the reason that I prefer this version is typically as a calculus question, when we're asked the equation of a line, it's almost always the equation of a tangent line, meaning I know I'm going to have to find a slope, and they had to tell me what point we were at. So that point I've already got ready to plug in. Now from there, if you want that to look like y equals mx plus b, we can manipulate that equation to look like a y equals mx plus b equation. I know that I have to start with 2 points. The point I was given and that fake point where I'm adding in a plus h. So the point that I was given here would be 4, comma, and then when I plug in 4, the square root of 4 is 2. That other point is going to come from 4 plus a little bit, and then plugging in that 4 plus h to the function. So square root of 4 plus h, which means our slope is going to be the limit as h approaches 0. My y2 minus y1 over x2 minus x1. So I'm going to give you 2 minutes on your paper to work out what the answer is to this limit. When we plug in 0, in the denominator we've got a 0, and in the numerator, when I plug in 0 here, I'll have the square root of 4, which is 2. 2 minus 2, I also have 0. 0 over 0 means go do some algebra. So I'm looking at the limit as h approaches 0. Because we've got a square root, I know that the algebra we want to do this time is to multiply by the conjugate. So I'll have a plus 2, and the square root of 4 plus h plus 2. In the denominator, that's the h that I'm hoping is going to cancel out. I don't want to multiply the denominator out. I want to leave it alone so that we can get that h to cancel. In the numerator, when I have square root of 4 plus h times square root of 4 plus h, I'll just end up with 4 plus h. Those middle terms cancel. That's why we multiplied by the conjugate. And negative 2 times positive 2 is going to be a negative 4. Once again, I've got my 4's canceling out. That h over h is going to turn into a 1. And when I plug in 0 for h here, I'll have 1 over the square root of 4 plus 0 plus 2, or 1 over square root of 4, that's 2 plus 2, 1/4. Well, we did this at 1 and we did this at 4, but what if generically I just called this x? Well, that would make my y value f of x, or in this case, the square root of x. And if I move over a little bit of h, then I would be at x plus h. And if I came up here to get to the y value, my y value would be at f of x plus h. Or for this particular function, that would look like the square root of x and the square root of x plus h. So if I want to find a rule for the slope of the line tangent to the curve without picking a particular value of x, then we can follow the same idea that we've been doing. We're just going to leave all of those x's in it. And I realized I might need a little bit more space here. So I'd be looking for the limit as h approaches 0. Still going to do a change in y over a change in x. So I'd have the square root of x plus h minus the square root of x. My denominator would look like x plus h minus x, because again, I'm looking at that change in x. And because this happens every time, that minus x and that plus x cancel out. Now, if I plug in 0 for h, in the denominator we get 0. In the numerator, when I plug in 0 for h, I have the square root of x minus another square root of x. Square root of x minus square root of x is still a 0, which means I still have to go do some algebra. And because I have square roots, the algebra that we're going to do is to multiply by the conjugate. Multiplying by the conjugate here looks a little bit messier at first, but it's not a whole lot messier. I'm going to leave the denominator alone, again, because I want that h to go away, so I don't want to distribute it in. And in the numerator, the square root of x plus h times the square root of x plus h is x plus h. Middle terms cancel. The square root of x times the square root of x, negative square root of x times positive square root of x is negative x. Same trend as what's been happening in those the other times we've done this where we had numbers in there for x. These cancel out. I have h over h, which is going to give me a 1. So I have a 1 in the numerator, and in the denominator, I'm ready to plug in 0 for h to get the square root of x plus another square root of x. Or sometimes we write that as 1 over 2 times the square root of x. This thing right here, that's giving us the rule for how to find the slope at any given x value. And we have a special notation for that. And the special notation that we use is an f with a little markup there. And we call this, we read that as f prime, not Amazon Prime, but f prime. We read that as f prime. And we call this the derivative.